you're losing that material. At that time, in the same time frame of rate of change, the daughter products are increasing. And of course, when they've reached this interval right here, this intersection point, that's the point at which the rate of change of decreasing the parent, rate of change of increasing the daughters is exactly the same, and that would be exactly one half-life, you see, at that point. Okay, what will affect this change? Oh. Another technical problem, huh? Yeah. I don't know, Brian.
Tech support.
It's on my screen.
Turn your screen around.
I think it's off. Yeah. I don't know. It's not my equipment. Okay. There it is.
There you go. Play with the red button.
We're in the countdown now, so. There we go. Okay, let's hope this continues in a good way. So what affects these decay rates? In other words, can they change? That's one of the things we have to consider, right? The progress of the decay process in time, of course, we said was the measure of the decay rate, wasn't it? And of course, that's the thing that we're looking at. What is that actual mechanism causing that to happen? And can that mechanism be altered? Selecting a radioactive isotope, if we subject it to an environment where there's extensive amount of energy, enough to interact with the energy in the nucleus of the atom, then it will cause the decay rate to be accelerated. Now we're talking about a lot of energy, an enormous amount of energy, but the question is it possible for that to happen? Okay, well, in the process, as we discuss it, the nucleus of the radioactive isotope will emit one or more particles, and usually it's either called an alpha particle or a beta particle, by and large, or sometimes it's a positron. Now, alpha particles are not defined here, but if you took a helium atom and you stripped all its electrons away, both of them, there's only two, you would have the helium nucleus, which is an alpha particle. A beta particle is simply an electron that comes out of the nucleus. And the positron is the so-called antiparticle of the electron, which is the positively charged electron, the positron. Okay, so these are the main ones that are released in radioactive decay. Sometimes there's other things that happen once in a while, but by and large, it's restricted to these three types of particles. So they will cause that parent isotope to be transformed into a new daughter isotope. Okay? So here it is. Energy is being given off in the process. Of course, radiation is always happening because energy is changing, so you're going to have radiation. And then, of course, the particles are coming out at a certain accelerated rate. And that's the whole mechanism of that decay process. So if you imagine all of this going on as each little nucleus of each atom is subjected to its environment, then all these processes are happening, and then those processes can be affected by the environment. Here's some examples of decay changes. For example, uranium-238, that's this one here, isotope number 238. It has a 4.5 billion year half-life as determined indirectly in the laboratory. Nobody sat around naturally for 4.5 billion years trying to watch that half-life, right? I know I'm pretty old, but I haven't quite gotten that old yet. But that's what they call an extrapolation process, and they usually extrapolate it in terms of the energy. So each decay process has a finite amount of energy, and as that energy changes with decay, that's how they get these half-lives. Okay, there's a helium nucleus, which is an alpha particle, electrons, which are coming off, which are beta particles, and then you end up finally, after quite a few unstable isotopes down the line, you end up with a stable isotope of lead, number 206. Uranium-235, a different isotope of uranium, undergoes a similar decay. It's a little bit shorter, 0.71 or 0.713 billion years for its half-life. And that also gives alpha particles, the helium nuclei,